Welcome everyone to our next N3AS seminar of this lovely spring semester. And today we're very happy to have Kohta Murase from Penn State and the Institute for Advanced Study. And Kohta will be telling us about high energy multi-messenger emission from supermassive black holes. So please, whenever you're ready, take it away, Kohta.
Okay, thank you very much for the invitations. I'm happy to talk about our recent results and application of the neutrinos from the active galactic nuclei. So that I'm now the IAS for the sabbatical, and then it's good time to talk about these. Okay, well, it's freezing somehow. Okay, that's coming. So the high energy neutrinos have been measured, and since the discovery by the IceCube, and then now that we see the high energy neutrino events in all the direction in the sky. And then if you look at the neutrino sky, we see that the distribution is consistent with isochronic distribution, and which suggests that neutrinos mostly come from the extragalactic sources. And then although it might be some contribution from galactic sources, but I would like to focus on the extragalactic population. And then IceCube measures the neutrino flux, I mean the all sky neutrino flux. And then this is a spectrum, and then as a function of energy, and we see that the neutrino energy flux is order of several times 10 to the minus 8 GeV per centimeter square per second per radian. And then we have measurements from using the muon neutrino tracks, and we also have a measurement from the showers, basically cascade caused by neutrinos, electron neutrinos, tau neutrinos. And then so far as the data are consistent with the power distributions, although we do not exclude the existence of structure, but we have not found any evidence for such structures like a hardening in the Q100 TV or something like that. And then we have not found extremely high energy neutrinos above above 10 PV regions. And we have upper limits on the ultra high energy neutrinos. And then one of the big questions in neutrino astrophysics is where do these high energy neutrinos come from? And then people believe that these neutrinos are produced by the energetic, powerful extragalactic sources, which include the gamma ray burst, which is actually the most powerful explosion in the universe. And other people think about the active nuclei, galactic nuclei, in which the supermassive black holes are powered by the supermassive black holes with jets, or some accretion disk, and galactic clusters, or which are the largest gravitational bound object in the universe. And then there are some people consider the neutron stars or magnetars with a strong magnetic field over 10 to the 15 Gauss or something like that. So in these astrophysical sources, and we expect that high energy neutrinos are produced by the cosmic rays. So main production channel for the high energy neutrinos are believed to be proton-proton interactions or proton-gamma, P-gamma interactions. For example, if you think about the luminous sources such as active galactic nuclei or gamma ray bursts, because these objects are so bright, and we see there are a lot of photons in their different wavelengths in the optical or X-rays or gamma rays, and these photons provide their copious target photons for the P-gamma interactions. The very energetic protons, which are cosmic rays, can interact with these low energy photons, the field that mostly delta resonance, and making pions. And if you think about galaxies or galaxy clusters, in these environments, and the cosmic rays can be confined in these systems. That's the reason why we sometimes call the cosmic ray reservoirs, because in these objects, the cosmic rays can be confined for many, many years. For a long time, during the confinement of the charged particles, the protons or nuclei can interact with the gas inside these objects, making pions. So in any case, proton gamma, in either case of the P-gamma interaction or PP interactions, the cosmic rays produce charged pions, and the charged pions eventually decay. Where in interaction, you have neutrinos. This is actually the main production channel for the neutrinos. So not only neutrinos, but also gamma rays should be produced. However, the fate of gamma rays is more non-trivial because high energy gamma rays cannot avoid interaction with the cosmic background radiation field, which include CMB and X-ray background light, including the cosmic optical background, infrared background. And then these high energy gamma rays interact with the cosmic background radiation field and make electron positrons, and then the high energy gamma rays are attenuated. But this is not the end of the story because the electron positrons can still upscatter the background radiation fields, and eventually which cause electromagnetic cascade. And the cascade gamma rays actually eventually can be detected at lower energy gamma rays. And you can also use the cosmic rays, but the cosmic rays are charged particles, they are deflected by the magnetic fields, and then it's not so easy to know the direction of the cosmic rays by the direct measurements because of magnetic fields. So, however, it's important to use all the different messengers because each messenger brings us information. And indeed, we observe all the three particles and the diffuse flux. This is actually the spectrum of the three messenger particles at the functional energy. And we see that gamma rays, neutrinos, and cosmic rays. And we can find that the energy flux is more or less comparable, which means that the energy generation densities of the gamma rays, neutrinos, and ultraviolet cosmic rays are comparable, which may indicate the possible connection. However, we don't know the origin of the neutrinos and ultraviolet cosmic rays. On the other hand, we more or less know the origin of the X-ray gamma ray background. So if you look at the X-ray gamma ray sky, then this is the Fermi sky, that we see the galactic plane, and we find many point sources in the high latitude. We know that they are mostly blazars. Blazars are AGN whose jet point towards Earth. And then, especially above 10 GeV, at least 50% actually believed to come from the jetted AGN. So it's quite natural to expect that the neutrinos also may come from the blazar object. And then, but people actually look for the neutrino emission from blazars, but the answer is not so trivial. So because if you use the stacking analysis, at least if you use the gamma ray stackings, and then the blazars, and because the blazars are so bright in gamma rays, the stacking analysis are powerful. And then you can always some correction for the sources which are not detected as a point sources. But even if you take into account these populations, and it seems that the blazars are subdominant in the diffuse neutrino sky. So this implies that we need something different population, some different population to explain the dominant fraction of the ISQ neutrinos, especially in the 10 TeV range. So in this case, actually, we can go back to the original the plot, and then we can ask what is the generic connection between the neutrinos gamma rays. So that if you think about the process of the neutrinos, if you want to produce neutrinos, okay, so I think that we should use that data pointer. If you want to produce neutrinos, and by either PP or P gamma interactions, in either case, charged pion are produced, but neutral pions also should be produced. And then gamma ray production is unavoidable. And as I told you, that these gamma rays eventually cascaded down to the intergalactic space if they escape from the sources. So you can actually try this kind of exercise. So if you want to explain the ice cube neutrinos, then you can ask what is corresponding the flux of the gamma rays, right? So that these are, for example, let's think about the PP line in the dash curve. And if you want to explain the neutrino data by PP interactions, then you also have gamma rays. And the gamma rays come from the neutral pions, they eventually cascade down the intergalactic space. And then if you compute these, basically we find that the expected gamma ray flux actually in the tension with the observed Fermi in isotropic diffuse gamma ray background. You see that this dashed line actually is exceeds the contribution from the non-brazier, the basically non-point source contribution of the eccentric gamma ray background. So this is true that even if you consider the P gamma sources in the minimal scenario, so basically if you do some sophisticated analysis, you can find that if you assume that the gamma rays escape from the neutrino sources, then you cannot avoid the tension with the observed gamma ray background with this, at least 3 sigma level. So this implies that if you want to avoid this tension, you need something that you have to block the gamma ray somehow. So you need a hidden neutrino source in the sense that if you want to explain the neutrino data in the, especially in the 10 TeV range, that you need some gamma ray opaque sources in which the gamma rays are attenuated inside the sources rather than outside the sources. So is this natural? And I think that it's not. This is not so strange, because, for example, if you think about the P gamma scenario in which the neutrinos are produced by the interactions between the protons and photons. In this case, neutrinos are produced by, you can compute the efficiency of the photomeson production, which is the optical depth. But the same target photons required for neutrinos are also dangerous for the gamma rays, because the gamma rays can interact with the gamma-gamma interactions. So the cross-section ratio is about 1,000. So this means that if you want to have a neutrino productions in a reasonable efficiency, basically gamma ray, so the efficiency of the gamma-gamma interaction, basically optical depth for the gamma to photon annihilation process must be very efficient. So basically if the efficiency of the neutron production is larger than 0.1 or 0.01, basically the system has to be optically thick. So this is actually kind of implies that it's natural to expect the hidden neutrino sources in a sense. So which kind of sources can be responsible for the hidden sources? This is a question that people think about the black holes, the vicinity of black holes, or jet embedded supernova. And then the question is that, okay, so this is the implication diffuse flux that do such hidden neutrino sources exist? And then this is actually interesting question. But now the last 2 years, so the IceCube has an announcement, and then reported the evidence for the neutrino emission from the nearby active galaxy, the N3AS. Actually, these sources are quite interesting. That this is actually one of the examples, a good example of the hidden source. So I'd like to explain this kind of implication of the N3AS from now. So this is the result. I took this plot from the science paper, which is published in the by the IceCube collaboration, and then so the IceCube is actually the collaborations look for the hotspots and in the neutrino sky, and then they actually did 3 different analyses, but one of the they at least they found that look for the brightest hotspot in the neutrino sky, which actually turned out to be the coincident with direction towards the N3AS. And they also tried the search using the predefined catalogs, which mostly consists of the gamma ray sources, and they use the 110 sources, and they found that the most significant source turned to be the N3AS. And then they reported the 4.2 sigma as a posteriori, and then in the direction towards the N3AS, they found about 80 excess events, and it's quite impressive that they see that this kind, they provided this kind of plot in the neutrino observations. So they also this is the spectrum, and the spectrum of neutrinos actually turned to be the relatively soft, and then this is actually the spectrum, which is indicated by the blue shaded round, and then you can actually also plot the gamma ray data from the Fermi gamma ray telescope, and then the magic also place the upper limits in the TV range. So you can immediately find that the observed neutrino flux is much larger than the gamma ray flux in the Fermi, and upper limits are reported by the magic collaboration. And then I also show that the neutrino flux actually from the models, which I explained later. But at least this actually already has an interesting implication. So that this NC1068 is actually known to be the prototype safer two galaxies. Basically, it's one of the AGN with weak jets, so they don't have it doesn't have a powerful jet, and then this is known to be one of the starburst galaxies. But if you consider the starburst galaxies as a neutrino sources, you should expect that gamma is actually with a similar flux. So this is actually indicated by this prediction is indicated by this line. And then if the neutrinos actually come from the starburst galaxy, starburst activities, you should expect the gamma rays and neutrinos are comparable, but you see that the neutrino flux is larger than this, and then this implies that you need to invoke some region to produce more compact regions to produce neutrinos. Okay, so what happens in such a more compact region, the active galaxies? So the people believe that the active galactic nuclei actually have the action disk and with a high temperature corona. So people see the blue bump or some of the blue optical ultraviolet emissions from the accretion disk, and we also see the X-rays coming from the corona in the high temperature corona, the upscattering by the very energetic electrons. There's such coroners actually also start to be seen in the recent numerical simulations. And once you think about such a vicinity of the supermassive black holes, because we expect that intense radiation fields coming from the action disk, which is the optical to ultraviolet, and we also have X-ray photons from the corona, and these photons actually naturally provide the target photons for the photomeson productions, and then you can expect the efficient neutrino production in such regions. So then in this case, the NC1068 actually we expect that such intense radiation fields from the observations in the optical ultraviolet and X-rays. And then, for example, the new stars actually has a measurement of the X-ray. This agent is actually known to be a Compton-6 agent with a high Coulomb densities. Basically, this agent actually embedded the very dense gas and dust, and a lot of X-rays are attenuated. And actually, it's not so easy to guess what is going on in the vicinity of a supermassive black hole. But if you look at observations, intrinsic X-ray luminosity is actually the order of the several times 10 to the 43 erg per second, and which is consistent with the estimate on the barometric luminosity of the 10 to the 45 erg per second. So then if you actually use the information, that you can compute the gamma optical depth as a function of the gamma energy. This is actually the approach. So that you find that this actually depends on the emission radius. But for example, if you think about the very large emission radius, say the 10 to the 4 supersymmetric radius, in this case, GB gamma is escape. But if you allows the GB gamma escape, basically you violate the Fermi data. So in order to because the fact that this NC1068 actually should be the hidden neutrino sources, at least you need to require that the gamma optical depth has to be larger than 10 for the Fermi range in the Fermi band. Then this simple estimate actually based on the gamma optical depth actually that allows us to place our upper limits on the emission radius, which is about 30 to 100 Shivers radius or something like that. I can actually make this argument can be more can be checked with a more detailed calculations using the taking into account numerical taking into account the electromagnetic cascade numerically. So basically you can actually this is actually the single source version of what I showed for the diffuse flux, right? We see the neutrino. I still provided the neutrino spectrum data. Then you need to explain this data then by either by P gamma or PPA mechanism. But in either case, the gamma rays must be created, but these gamma rays must be cascaded down inside the sources. Then in order not to violate the Fermi data or magic upper limits, then you can actually argue that the emission radius of the neutrinos has to be sufficiently small. And then for example, in this case, I show the neutrino flux for the different emission radius, 30 Schwarzschild radius, 100, 300 Schwarzschild radius, and 10⁴ Schwarzschild radius. Then, for example, if you assume that large neutrino emission radius, the gamma ray flux actually automatically violates the gamma ray data. So in order to not to violate the data, basically the neutrino emission radius has to be compact, and then this is actually found to be the 30, at most 30 to 100 Schwarzschild radius, which actually confirms the simple estimate by the order of magnitude estimate. So the conclusion is that the model independently. So the fact that the neutrinos N3AS hidden source implies that the neutrino emission radius has to be smaller than the 30 to 100 Schwarzschild radius, maybe the 10 Schwarzschild radius or so. So then, okay, that's good. And then the question is that next question is that okay, what is the model? What is the picture of the neutrino production? This is actually not so known yet, but people actually consider traditionally the people consider accretion shock. Basically, in this case, the accretion material is actually free falls and forming a shock. But this picture is now disfavored or excluded by the extra observations. So usually many people think that the corona is actually formed by the magnetic activities. And because in the accretion system, because the angular momentum, we have actually some instabilities, so-called magnetic rotation instability (MRI), and then this actually the instability is actually accompanied by dissipations, and eventually it causes reconnections, and basically some magnetic energy is actually converted to the heat, and which actually may explain the corona. And then other models actually try to invoke the field winds, and then we expect that the winds actually launched from the accretion disk. And then if the wind velocities that does not reach the escape velocities, that sometimes they fall back, and then we can have some shocks. That this is actually one of the possibilities. And then predictions are actually different, depending on models. But so far, it's not the two models actually for the field wind model, the magnetic corona models. It's possible to explain these. But I think that in the corona case, it's actually possible to study in more detail, because now the numerical simulations actually the techniques actually quite advanced, and there's a lot of progress in the techniques of numerical simulations. For example, I show the results of the test particle simulations. In this case, we did a simulation of the magnetic rotation instabilities, and for the snapshot of the simulation result, we can actually see the stochastic particle acceleration happens. In the case of energy 1068, it's interesting because if you think about the stochastic acceleration, which is essentially the second order Fermi process. Second order Fermi process is slower than the shock acceleration of first order Fermi acceleration process. If you compare the acceleration time, and in this environment, because a lot of photons come from the disk, and which is actually the important energy loss process, base hydra pair production. Basically, protons and interact with photons and produce the pairs. This is actually the main energy loss processes. And then if you compute the maximum energy of the proton, which is actually around 100 TeV, which is consistent with the maximum energy of neutrinos around 10 TeV, dozens of TeV, or something like that. Then, in this sense, actually, the slow acceleration scenarios might be compatible with ice cube neutrino data. So the NC1068 are also kind of interesting because if safer galaxies are actually such a populations exist in the whole universe, and it's actually possible to explain the diffuse neutrino data around the 10 TeV to 100 TeV. So in this sense, this model can naturally explain the neutrino data from the 10 TeV to the even PeV. That's actually interesting. And then the question is that what is the testability of this kind of scenario? So now of course, ice cubes are going to keep observations, and then we will have more statistics because this is steady source. But the chemistry net or BICAR-GBs can also would also be helpful to test this kind of model. So for example, because the NC1068 actually is found to be one of the brightest X-ray, brightest AGN, the intrinsic X-rays. So the intrinsic means that because this is compton-thick AGN, that we have to collect the absorption by the gas. After the collection, basically NC1068 is actually the brightest in the switched catalog in the 2T hard X-rays. And then this also explains why the NC1068 is actually popped up the most significant source. But if you look at this catalog, okay, so you can find other candidates that maybe this kind of sources may be important for the next generation neutrino telescopes like ice cube Gen 2. And also if you look at X-ray data, and you find that more interesting sources actually exist in the southern sky. And then this is actually interesting for chemistry nets. So if you with chemistry nets, maybe Sachinus galaxy or other compton-thick AGNs may be detected in the catalog searches. That's actually one of the interesting tests. Also, even in the ice cube data, the ice cube already did the stacking search, and these are kind of tentative evidence for the the neutrinos from AGN. So that actually with more data, this kind of the scenario might be tested. Also, if neutrinos actually produced by the PP or PGAMMA scenarios, as I told you, that because emission radius has to be compact, but in this case, eventually the gamma ray energy must appear somewhere, and this is actually should be in the MeV range. And then so far that we don't have a good MeV gamma ray telescope, but once we have a gamma ray detectors, actually good gamma ray detectors, which is includes Amigo X or Astrogram, it's possible to test this kind of scenarios using gamma rays. So this is actually a good test. Okay, so now actually I already explained the implication of the NC1068 and some models. Using the 5 minutes, I think that I just would like to mention the other possibilities, including transients. So the supermassive black holes, and then the AGNs are thought to be neutrino sources, and some of the AGNs have a powerful jet. Several years ago, the ice cube reported neutrino detection from the Brazier TXS0506, and then they found one event which coincided the multimesssenger flare, and they also look for the archival data, and they found the 30 events excess in the 2014-2015 that this is an orphan neutrino flare. Because at this time we don't see the flares in the electromagnetic waves. And then, unfortunately, in this case, actually, we don't have good theoretical pictures at this point, because we can do the similar exercise, right? So if we have neutrino data, And then we want to, if we want to explain the neutrino data, that you can compute the gamma ray data. You can calculate the gamma ray flux. But the gamma ray flux, expected gamma ray flux, is more or less comparable to the neutrino flux. But in this case, for example, this is actually more clear for the 2014-2015 neutrino flare. Basically, the expected gamma ray flux is actually larger than the upper limits, especially in the X-ray range. So in order to not to violate the observed data, yes, you need to mask the gamma rays, but or X-ray, but it's not so easy to mask these X-rays, gamma rays in the simple manner. So at least the standard single zone model does not work. And also this kind of case, actually, we have a severe energetics issue, and which is actually also problematic in light of the theory. So the story is actually not so simple. And then the people actually look for the more coincidence, and the answer is yes. And then we have more coincidence, and which includes PKS 11502 or 3S, the several more coincidences have been found. But the situation is actually similar. So basically, if we want to explain the neutrino data, yes. So in principle, you can have gamma rays, but you have some tension with the gamma data, or you have some energetic issue. So of course, you can think about more beyond, you can go beyond the single zone model. So you can actually think about 2 zones, 3 zones, but in this case, you have more parameters. And then it's not like obvious that how we can test this kind of the multi-zone models. Okay, so this is what's the coin? Okay, this is a summary. So so I first explained that multi-messenger analysis actually indicates the existence of the hidden cosmic accelerators, which is especially true if you rely on the neutrino data in the 10 TeV range. And indeed, such a hidden neutrino source was indicated from the NHC 1068. And then because the neutrino flux is higher than the gamma flux, and then emission radius of neutrinos has to be very small, and then within the at most 30 to 100 Shepard radius. And then safe-hard galaxies or these AGN with basically jet-quiet AGNs actually can explain all sky neutrino flux without any issue, and as a dominant sources. And then if this model is correct, we may expect a more such hidden source in the southern sky, which is very interesting for the chemistry net of microgravity. And then the IceCube Gen 2 or ME gamma satellite observations also important. And then jetted AGNs, actually blazars, also kind of interesting. But so far as we have several coincidences, but so far we don't have a good simple pictures. And then we can invoke the more complicated models, but testing them is actually quite important. We need more data. So thank you very much for paying attention.
Thank you, Kohta, for that very interesting talk. Do we have any questions for Kohta? If you do, please raise your hand using the Zoom feature. And I see we do have a question from Wenbin Wu. Please go ahead.
Hi, Kohta.
Yeah,
Good to have you here. I have a question. So I haven't really worked on this neutrino, this NGC 1068. It's really interesting. So I wonder about this broadband SED. So you're saying that it's Compton thick. So the bolometric luminosity would be obscured, whereas that luminosity will be re-radiated in the infrared band, right? If the bolometric luminosity is, it's a very high, 10 to the 45 ergs per second, we should still see that. So is that still consistent with the infrared flux? Let's say 10 to the
yes,
minus
I think
9?
that I think that it's consistent with the infrared flux. I think that it's not all, because still actually that you have to think about the redistribution. Actually, there are several ways to estimate the bolometric luminosity. Some people actually use the line emission. And then because we see some scattered line emission, based on the relationship between the line luminosity and the barometric luminosity, actually they do estimate. We also have infrared emissions, and some fraction, good fraction of the emission should be actually radiated as an infrared emissions, and this also actually the consistent with the barometric luminosity of the 10^45 a second. Indeed, it's actually that we have infrared observations, but even infrared actually this is a very complicated system, and I would say that the estimate of barometric luminosity still has an uncertain factor of 10 basically, but cannot be too small. Cannot be too small.
Yeah,
it's actually 10^45 even more.
Yeah, exactly. If it is a Compton thick, then nearly all photons are completely absorbed. Like all optical photon, X-ray, and so on, they're completely absorbed, and then they should re-radiate in this 1 eV or a little bit less than 1 eV.
Yes, I think that it's actually yes, indeed this happened. Also, it's actually but eventually because AGN is actually not completely spherical, right? You have some hole, right? And eventually some X-rays are scattered, and then this actually depends on the geometry. And then, but we actually, for example, new stars actually has observations in such a scattered emission. Then based on the modeling, and then you can estimate the intrinsic X-ray flux. And this is actually the barometric luminosity estimate from the X-ray observations, also consistent with 10^45 a second. So I think the infrared, the optical, X-rays, different observations indicates a similar estimate of the barometric luminosity. In this sense, it's quite reasonable.
I see. And this one is really energetic. It's so nearby. It's the most energetic hidden AGN, right? Nearby. We didn't even know this before the neutrino discovery, right?
Yeah, I think that, for example, if you believe there's a black hole mass estimate, if you compute the Eddington parameter, right? So the Eddington parameter actually is 0.3 to 0.4, and then it's nearly Eddington system. That it's quite powerful.
Yes. Thanks.
Next, I see Zidu Lin. The floor is yours.
Yeah. Okay. Thank you so much. First, thanks so much for your interesting talk, Kohta. So actually, I have a question relating to the neutrinos. So I see that those neutrinos are actually coming from the pion decays, right?
Yes, charge pion decay, yes.
Right. So from the pion decays, we not only have those electron type neutrinos, we also have those heavy flavor neutrinos.
Yes.
So my naive question is that what kind of the detector do you think, or maybe a future detector that we will have to detect the heavy flavor neutrinos from?
I think in this case, because they look for the muon neutrinos. So indeed, the IceCube actually detects the muon neutrinos. So in the charge pion decay, basically you have both electron neutrino, muon neutrinos. Eventually, the neutrino mixing happens. And then the neutrino flavor ratio on Earth should be about 1 to 1 to 1. So basically the muon neutrinos, electron neutrinos, tau neutrinos, the ratio is actually about 1 to 1 to 1. And then so the IceCubes in this search, they look for the muons. Then the muons actually created by the hit. If the muon neutrinos hit the ice, and you have muons, and the muons actually go through the ice, and eventually you see the chemical radiations from charged particles, by which basically IceCube is actually sensitive to the muon neutrinos. But you should also have electron neutrinos, tau neutrinos, and not in this search. For example, if you look at diffuse neutrino search, and indeed actually in the diffuse search, right? So that this is actually the shaded lines. Actually, this is actually result from the muon neutrino search. But shower search actually is mostly sensitive to the electron neutrinos and tau neutrinos. So that we actually, the IceCube already sees different types of the flavors.
I see. So if I understood correctly, are you saying that all these flavors of the neutrinos, they have about the same spectrum, or are there any difference between those neutrino energies or maybe the neutrino luminosities in different flavors?
Yeah, I think that this actually really depends on the models. So in that case, actually, in this Emission 1068, actually we expect that neutrino flux actually more or less similar because of neutrino mixing.
Okay.
Yes, but
Okay, I see.
if you think about the super dense sources like hidden jet in the supernova, in this case, in principle, you can have a different spectrum for the different flavors. Then that's
yeah, sure. So in principle, if we can somehow compare those neutrino spectrum from different flavors, probably the deviation might tell us something, but I don't know what exactly would be the things that.
Yeah, I think that
yeah.
Famous type of the example is actually this kind of system because sorry, how can I? Yeah, shock jet in supernova. In this case, you can have if you have neutrinos in a very dense environment, basically the neutrino flavors can be affected by matter effect or some cooling effect, and then in this case, the different flavors can have a different spectrum.
Okay.
Yeah, I can indicate the papers. We have some papers on this.
Okay. Yeah, sounds interesting. Yeah, I have my last question. So, which is about that pi decay reaction. Are we clear about that reaction? So, which means that this kind of the pi decay to a lot of different neutrino flavors. I mean, we can derive clearly about the neutrino spectrum from different flavors. For example, we can derive clearly about the electroneutrino flavors spectrum and the heavy flavor neutrino spectrum. We can derive them all clearly. There are nothing mysterious about this kind of the reaction.
Yeah, I think that I think that in strictly speaking, actually we have ambiguities from because we don't know which PP or P gamma, which is important, we don't know. So the PP, P gamma actually depending on the channels, actually the expected flavor races are affected. So in a sense, we cannot, we have some uncertainties coming from this production channel. But once you actually determine the PP or P gamma, then we can calculate the neutrino flux, at least within the standard model.
Okay. Yeah. Okay. Thank you so much. Okay.
Do we have any more questions for Kohta? I don't see any, so I'm going to stop the recording.